Hi everybody, this is another in my series of videos on computer systems. And this one will take a brief tour through I/O management and disk scheduling. This is another Module 9 video where we're just taking a very quick look at a few different topics just to get an idea of what kind of considerations we have to make when we're dealing with operating systems. Now in this video we'll talk about, again, input output. So there's several categories of I/O devices that we want to be aware of. We've got, and what an I/O is external devices that engage in I/O with computer systems. And we can group them into three categories. We have human readable, so that's suitable for communicating with the user, so printers, terminals, video displays. Machine readable, which is suitable for communicating with electronic equipment. That's things like disk drives, USB sticks, that kind of thing. And then we have communication devices that are suitable for communicating with remote devices like modems, digital line drivers, networking. Now, there are several differences in I/O devices, and they differ in a number of areas. Data rate, the kind of application they use, the complexity of control. A mouse is very simple. Disk I/O, maybe not so much. The unit of transfer, right? Are we talking a stream of bytes, characters, larger blocks? Data representation, we use different data encoding schemes when we talk about different devices. And we have error conditions, right? What kind of errors do we run into? How are they reported? What kind of consequences do they have? So when we're talking about I/O design, we've got several objectives that we want to keep in mind. We need to design them for efficiency, because I/O operations often form a bottleneck, right? This is where, when we talk about process control and things, when we go out for I/O, this is where we're blocking and we're waiting on things, right? So this ends up being a bit of a bottleneck, so we want things to be efficient. We want stuff to happen as quickly as possible. Because most I/O devices are very slow compared with like main memory or the processor. So that's the area that's received the most attention when we talk about disk I/O. And even way back in earlier modules, when we talked about the benefits of higher RPMs in spinning disks versus solid state drives, etc., this is all what that's about. We're trying to improve the efficiency and improve the speed with which we can get information from disks in that particular case. We also want generality, though, right? We want to be able to handle all devices in a uniform manner. There's a big diversity of devices, and that makes it very difficult. So we use a hierarchical approach to designing the I/O function because, I don't want to have completely different setups for every different kind of USB stick I want to use or every different kind of hard drive. We want to keep things general if we possibly can. So that hierarchical design basically says functions of the operating system should be separated according to their complexity, the characteristic timescale, and their level of abstraction. So we're going to organize the operating system into a series of layers, and each layer performs a subset of the functions required. These layers should be defined so that changes in one layer don't require changes in other layers, right? This is how we help keep things general. We layer things out and we separate out our functionality so that hopefully we can make small changes to individual layers without having to completely rework the whole hierarchy. Now, another thing that we want to keep in mind for I/O is buffering, right? Perform input transfers in advance of requests being made and perform output transfers sometime after the request is made. For a block-oriented device, we're going to store the information in blocks that are usually of some kind of fixed size. We transfer things one block at a time, and we can reference data by its block number. So disks and USB keys are things that we do with this. For stream-oriented devices, we transfer data in and out as a stream of bytes. There's no block, but terminals, printers, communication ports, most secondary devices, or most devices that are not secondary storage are examples of this kind of thing. So without a buffer, the OS directly accesses the device when it needs it, right? So the I/O device, everything goes straight to the process. We make a request as we need it. We get something back as we need it. We don't store anything. With a single buffer, the operating system assigns a buffer in main memory for an I/O request, right? So the I/O device sends things to that buffer where it gets stored until the user process needs it. We can also do double buffering, right? We'll use 2 system buffers instead of 1, and we can use basically switches, right? Every time we have new information, we move one block in, that gets moved to the user process, then we switch over to the next buffer to move the next block in, switch to the next buffer to move the next block in, and we just switch back and forth between these buffers. And that can actually be expanded to a circular buffer, right? So we can have a ton of buffers. We can have all the buffers we want, really. I mean, that's going to be a design decision based on system resources and just how we want things to operate. So we can just circulate our way through as many buffers as we like. We just start with the first one, go to the next, the next, the next, the next, and eventually when we get back to the end, right, when we get to our last buffer, we go right back up to the first one, and we just keep going in a circular way through all of our available buffers. And that same way, that just gets moved into the user process as we need them. So what buffering does for us is smooth out peaks in the I/O demand, right? With enough demand, all the buffers will eventually become full and their advantage gets lost, but that takes a while, right? The more buffering we do, the more buffers we have, the more we can kind of keep things flowing along, even when we have a whole bunch of requests going on. When there's a variety of I/O and process activities to service, buffering can definitely increase the efficiency of the OS and the performance of individual processes because, again, they don't have to block for so long. Instead of having to go all the way out to disk, I can just go to main memory. That's a whole lot faster. And that means that every process that has to block and wait for I/O doesn't have to go all the way out to that slow physical disk. It can just go to main memory. Now, when we deal with how are we processing requests to an I/O device, specifically in this case a disk, there's several different ways we can do things. So the first thing to do is, if you don't remember, refer back to how spinning disks work. That's in previous modules. And also you'll notice that we use some of the same ideas that we used in scheduling algorithms back in previous modules as well. When we talked about processor scheduling and real-time scheduling, we can use the same kinds of approaches when we talk about processing disk requests. So first in, first out, for example, processes everything in sequential order. It's fair to all processes, and it approximates random scheduling as far as performance goes, if there are many processes competing for the disk. And all this graphic shows you is if we're doing a first in, first out, as the read head, right, the read-write head goes back and forth across the disk, we're just going to process things as they come in. So we're not going to try to arrange our requests in a way to keep things more efficient. We're just going to put the processes in a queue, or the requests, I should say, in a queue, process them as we run across them. Now, our next possibility would be something like shortest service time first. And notice that we've actually cut down the amount of time it takes to service these requests in this way. What we do is select the I/O request that requires the least movement of the disk arm from its current position. So basically, we're always just going to choose the minimum seek time. So that might not be fair, right? We might process a request from some process later than another one. We're not going to process them in order. We're going to try to minimize the seek time to improve our overall efficiency. The scan approach, also known as the elevator algorithm, basically what we do is we talk about the arm moving only in one direction. Okay, it satisfies all outstanding requests until it reaches the last track in that direction. Then we reverse the direction that the arm is moving. So this is going to favor jobs whose requests are for tracks nearest to the innermost and the outermost tracks. But basically it just goes one direction, then back and forth, right? Now, C-scan, or circular scan, restricts scanning to one direction only. So when the last track's been visited in one direction, the arm just returns all the way to the opposite end, and the scan begins again. So it's similar to scan, except in scan, we're scanning during both directions of the arm movement, whereas with circular scan, we only scan in one direction and then just jump the arm all the way back to the other side and scan through in the same direction again. And all of these have different kinds of processes that they favor. They work in different ways, but it's just like scheduling algorithms we've seen before. Based on the kind of traffic we get, we can choose different scheduling algorithms to try to make things a little bit more efficient overall. The other thing that we want to be familiar with is something called RAID, which I'm sure you've heard before. What it stands for is Redundant Array of Independent Disks. And it's basically a set of physical disk drives that get viewed by the operating system as a single logical drive. Data is distributed across the physical drives of an array of disks in a scheme known as striping. And that redundant disk capacity is used to store parity information or even just entirely separate copies of all the information that guarantees some data recoverability in the case of a disk failure. So instead of having a single disk that has all my info, and when that fails, I'm out of luck, I can actually set up an array of disks and give myself some protection from the failure of any individual disk. Now, RAID consists of 7 levels, 0 through 6, although you'll see more than that when you kind of read about it or you hear about it. You might hear about things like RAID 10 or RAID 50. What those are actually combinations of these 7 basic approaches. So let's kind of just take a look through some of these to get an idea of what they mean and how they help us. So first of all, RAID level 0. Now, this isn't true RAID because it doesn't actually include redundancy to improve performance or data protection. The user and system data are distributed across all the disks in the array, and so the logical disk is just divided into strips. So we actually, in RAID 0, we're not actually talking about, we don't have redundancy. We're just basically taking a bunch of smaller disks and combining them into one larger logical disk by striping the data across them. With RAID level 1, we achieve some redundancy, but we're just going to duplicate all the data. Right? There's no write penalty. When we write something to a RAID 1, let's say we have 2 physical disks and we put them together into a RAID 1 array. Basically, when we write something, we just write it to both disks at the same time. So when one drive fails, we've still got the stuff over on the other one, and then we can rebuild the RAID, and off we go. Principal disadvantage of this is cost, right? I don't actually get any, not really compression, but I don't get anything extra. I don't, if I want a terabyte in a RAID level 1, I just have to buy 2 1 terabyte drives. I don't get to save anything as far as that kind of thing goes. It's pure duplication. So with RAID 2, we make use of a parallel access technique, and we stripe our data. We can typically use something like a Hamming code, and this is effective in an environment where many disks occur. So this one, we get ourselves some redundancy by using a Hamming code, so it's a little more cost effective than RAID 1. It's not really very widely used, though. RAID 3, we only have to use a single redundant disk, no matter how large the disk array is, and we use parallel access with data distributed into small strips, and we can get very high transfer rate with this. Okay, so we have, well, this is called bit interleaved parity. So in the event of a disk failure, all of the data is still available in what's referred to as redundant mode. So in this mode, the missing data is regenerated on the fly using an exclusive OR calculation, right? So because the data are striped in very small strips, RAID 3 gets very high data transfer rates. RAID 4, we make use of an independent access technique. We have bit-by-bit parity strip that's calculated across the corresponding strips on each disk. So the parity bits are stored in the corresponding strip on the parity disk. This has a bit of a write penalty when another write request of small size is performed, but it's another one. Now, RAID 2, 3, 4, you don't see a ton of it out there. The one that you do see very, very often is we see a lot of RAID 1, and we also see a lot of RAID 5. It distributes the parity disks bits across all of the disks. So the typical allocation is like a round-robin scheme like we see here. And what this means is that the loss of any one disk does not result in data loss. With RAID 5, we're back to where we've got some true failure recovery, and we don't have any kind of data loss whatsoever with a single disk loss in RAID 5. In RAID 6, we have 2 different parity calculations that get stored in separate blocks on different disks. So this gives us extremely high data availability although it does give us a substantial write penalty because each write affects 2 of those parity blocks. And the other nice thing about this, though, is we can actually lose up to 2 disks and still maintain all of our data, right? So however many disks we have, subtract 2, that's how many we need to keep up at any given time. So again, of these 7 different RAID levels, the 4 that are most commonly used are 0, 1, 5, and 6. And again, they can be combined. So RAID 10 isn't really a separate RAID level. We're actually combining RAID 1 and RAID 0. RAID 50 is a combination of RAID 5 and RAID 0. So that is just a brief look at kind of what RAID means, because we see it all the time, but I mean, we notice that a lot of people don't really know what we're talking about when we say RAID. They just know, oh, that's a disk thing that helps us out in some ways. So that is what we want to kind of take away from the chapter on I/O and file access.